Hi guys, for this week's MDE paper of the week, I chose this 2008 paper by Kulkarni and Reddy, an abstraction for reusable MDD components. It's actually quite an interesting paper. It's sort of a lot of the ideas are ideas that we pursued with Dogen, although perhaps we weren't too cautious about it. The fact that we're generating a code generator that keeps generating itself. So it'll be interesting to see what these two chaps have to say for themselves. It would be good to get a good technical understanding of what generation of generators really entails. I mean, we've already read a very good thesis by George, which was all about generating code generators, but I think we need more papers on sort of this sort of area. So anyway, without further ado, let's just have a quick look at the paper. So the title is An Abstraction for Reusable MDD Components, Model-Based Generation of Model-Based Code Generators. The abstracts. We discuss our experience of using model-based techniques to generate model-based code generators. The central idea behind model-driven development is to use suitable models to specify various concerns and transform these models to a variety of text artifacts. A business product needs to deliver a given business functionality on a wide variety of implementation platforms and architectures, thus necessitating multiple sets of code generators. Okay, this is interesting. I mean, I wouldn't say necessarily that this is the case, but it's an interesting statement. However, there is considerable commonality across these code generators. In the absence of a suitable abstraction for capturing this commonality, there is little or no reuse across these generators. Okay, right, now we're getting to the more interesting bits. I think this is probably worth a good old green. If we manage to get the green going. We present an abstraction for organizing model-based code generators as a hierarchical composition of reusable building blocks. A building block is a localized specification of a concern in terms of a concern-specific meta-model, model-to-model transformation, and model-to-text transformation. Okay, this is very interesting, and I guess this is similar to the idea of patterns. These concerns. I think we're perhaps highlighting a bit too much in our abstract, but it is an interesting paper. Model-based code generation is a 3-sub, so perhaps what we probably need to do is to delete a few of these. Model-based code generation is a 3-step walk over the composition tree, wherein the first step transforms individual concern-specific models into a unified model. The second step transforms the unified model into individual concern-specific text artifacts, and the third step composes these artifacts. Okay, this is very, very interesting. Again, I feel a bit bad for highlighting so much in the abstract, but clearly there's a lot of interesting ideas here. Right, so let's have a quick look at the keywords. So categories, subject descriptors, reusable software, reusable models, general terms, design, and testing language. Okay. Model-driven development, reuse, generative programming, meta level. So meta model, sorry. Perhaps we should highlight this tag. Right, so then, introduction. We discuss our experience of using model-based techniques for developing large transactional applications over the past 12 years. So this is a quite considerable experience, really. Implementation codes of a typical business application can be broadly classified into business logic code and code for solution architecture that addresses concerns such as design strategies, architecture, and technology platform. Okay, it's very interesting. This is a very refreshing paper because you can see that these writers, they have a lot of practical experience. The implementation is characterized by a number of recurring code patterns pertaining to data access, distributed architecture, presentation, transaction processing, etc. Okay, I think this is part of the same highlight, really. Based on this observation, perhaps we highlighted a bit too much. Apologies, we're messing around a bit too much with the highlighting today, but Sunday and everyone's slightly tired really, end of a long week. Based on this observation, we devised an approach wherein models are used to capture these patterns, and the set of high-level model-aware languages is used for specifying business logic, complex data access queries, GUI, event handling, etc. Okay, separating business functionality from technological concerns in model-based code generation result in a significant productivity and quality gains. Okay, this is a classic sort of claim that we always see in MDE, so we're not going to worry too much about that. In our experience, each business application required a different solution architecture. Since model-based code generators deliver the desired solution architecture, this necessitated extensive customization of model-based code generators. As a result, the tools team became a bottleneck as the approach can increase adoption. To overcome this problem, we thought of using MDD techniques. So I think probably worth highlighting this bit here. I mean, this whole paper seems to be one big highlight, but as a result, the tools team became a bottleneck as the approach gained increased adoption. To overcome this problem, we thought of using MDD technologies for developing model-based code generators. We developed an abstraction for organizing model-based code generators as a hierarchical composition of reusable building blocks and generated implementations therefrom. Right, this is quite an important highlight, so this one we might go for a different color. I think it might even be pink if PDF Tools allows us. Section 2 describe, in fact, to be honest, we haven't actually written any notes yet, so that's the I guess we could probably start with the abstract gist of the approach. So what we're saying here is the paper describes a method for generation of code generators based on a meta model. Probably need autofill mode. So it's based on a meta model. Actually, we need to code generators as a hierarchical composition of reusable building blocks. So it's interesting here, really. If you think about it, that's not far from what we've done, in the sense that we do have a composition of reusable building blocks. However, what we did instead of what they've done is we proposed the generation of we proposed the dimensionality, to create the dimensionality and to create two separate models for representing the building blocks versus the sort of the design aspects, what we call the logical model. So it'll be interesting really to contrast the two approaches really. The building blocks provides the specification for concerns. So a building block is a localized specification of a concern in terms of a concern-specific meta model. So the concern-specific meta model, so a building block is a localized specification for a concern specific Right, this is interesting. Let's make sure we capture this correctly. A building block is a localized specification of a concern in terms of a concern-specific meta model. Right, so I don't think, I mean, this is difficult to parse, but what they're trying to say here is that it's a localized specification. Let's just stop at the localized specification. So this is similar to our concept of a physical space. And then propose authors, propose a 3-step approach. First step is transform individual concern specific models into a unified model. I guess this is what we'd call our logical model. Then transform unified model into concern specific text artifacts, and finally composition of the artifacts. So this is fairly common approach. I guess you can leave it at that. The note we had here was, yes, I think this is quite an important thing. Actually, I don't really need one of these notes. I need org notes. Solution code patterns. Authors identify a separation of code into 2 types. Business or domain specific and architectural. In the architectural, clearly my copy and pasting is also a bit tired. So in the architectural, for the architectural code, a number of recurring patterns appear. These are effectively what we have identified as, so we call these SRPs, I believe, schematic repetitive patterns. Okay, cool. So up to now we've more or less aligned with these chaps. Now then, let's go into section number 2. Model-based code generation architecture. In our approach, application specification comprises of extended UML models, business logic in terms of a high-level programming language, Q++, and data accesses in terms of an extended query language, as shown on figure 1. We extend the UML models with the appropriate properties and associations to specify design strategies such as object-oriented mapping, auditing, concurrency management, logging, etc. As seen from figure 1, different code generators are able to deliver the same business functionality on different technology platforms. Now, I would like to highlight this bit here. Now, if you have a quick look at figure 1, I think we're going to see a lot of this is a classic approach, really. It's Q++, design strategies, extended UML models, and query code. All this gets munged up. Presumably this is the original implementation without the MDE. This is despite these platform-specific code generators sharing a great deal of common functionality and differing mostly only in the primitives offered by the target technology platform, e.g. syntax differences of programming languages, data type differences of databases, etc. Even when delivering identical business functionality on identical technology, platforms, different code generators are needed to deliver onto different architectures, e.g. synchronous queue-based messaging, etc. Similarly, well, I think we probably want to capture this bit. Just a highlight would do. Similarly, use of different design strategies results in different code generators. In the case of design strategies, the problem is exacerbated even further. Since many design strategies cut across several architectural layers, changing as an existing design strategy or adding a new design strategy requires modifications to multiple code generators in multiple places. Ensuring complete and consistent implementation of such a change requires thorough knowledge of all the concerned generators on the part of the tool implementer. This problem becomes more acute as the number of variants of the code generator grows. Now, I'm kind of skimming through a lot of this because, of course, you see that their problem is very specific to their implementation. They have a lot of code generators, and we don't really have this problem. We're more interested in the solution they came up with, but not because we're experiencing this problem. So I'm just going to skim through the bits of describing their problem. The tangling of model-based code generators as shown on figure 1 is due to the lack of separation of the various concerns, namely technology platform, architecture and design strategies, and the cross-cutting nature of design strategies. An improved architecture for model-based code generation is where the models are successfully refined through application of the various design strategies to a stage from where a platform-specific implementation can be realized through a simple task of model to text transformation. Okay, we all agree on that. That's exactly what we did. As the platform-specific code generators are independent of design strategy-related issues, the same model to text transformation specifications can be reused with different design strategies and vice versa. This separation of concerns enables a tool variant to be viewed as a composition of design strategy and technology platform aspects of choice. In other words, variability. Building block is an abstraction to support the separation of concerns and composition. Right. So presumably building block is going to roughly correspond to what we call a facet, I think. Building block is an abstraction that supports a generic model-driven. It's interesting that we don't have any prior work in this paper. They just started straight talking about their problem. So I think we're probably worthwhile using the highlight here. I'm giving it a green. At some point we're going to get this to work. Now I think we should also say that building block, the unit of abstraction and composition they propose is the building block. Presumably this is close to what we call a facet. So a building block is an abstraction that supports a generic model-driven code generation architecture shown as figure 2. Let's have a look at figure 2. So we have a meta model, we have an instance, meta model, and then we have multiple meta models here. Then we have the unified meta model there. Oh, this is just a classic sort of M0, M2 sort of diagram. What's different here is that we start talking about text. And then we have the text composition. Right, so the text composition roughly would be... Let's have a look at what they're saying about this. A building block is a localized specification of a concern in terms of a concern-specific meta model, model to model transformation, and model to text transformation. I mean, we've seen this already, but... Building blocks are composable, enabling a model-driven code generator to be organized as a composition of a set of reusable building blocks, each encapsulating a specific concern. Now, this is clearly what we call a facet. Excuse me. We can go for pink here, if Emacs would allow me. I think something went wrong with our highlight here. Let's try again. Nope, it just doesn't like it. So, figure 3 shows the building block meta model. A building block is essentially a means for expressing how a concern specification is transformed into models in code. Model-driven code generator is specified as hierarchical composition of building blocks of interest. Building blocks are of two kinds, leaf building block and composite building block. The instantiation, let's have a quick look at figure 3 then. So there's the building block. There's a composite building block and a leaf building block. Then you have some kind of weaving going on here. And so the building blocks are generic to all different kinds of meta model items. The specification of a leaf building block specifies how to stamp out the model elements of the unified model from the concerned specific models, and the transformation specification captures how the model is transformed into code. Right. We use QVT language. Apologies, let me just go back to this. The instantiation specification is a leaf building block specifies how to stamp out the model elements of the unified model from the concerned specific model, and transformation specific. Okay, right. So that says how we convert the building blocks. We use QVT language to specify the former and MTT language to specify the latter. Okay, pretty standard technologies rather than rolling your own as we did. A composite building block specifies how to compose its child building blocks. Composite building blocks may specify how to merge model elements stamped out by the child building blocks, if any special merging is required. We use the default key-based merging strategy of QVT, i.e. two elements that have the same value for key project properties are merged together. Interesting. Because we have exactly a similar approach for merging when it comes to variability. Let's put a note here. QVT merging, so default merging strategy. Not sure why it's so far away, but in QVT, the default key-based merging strategy means that two elements that have the same values for key properties are merged together. It's not quite what we're doing, but similar. Give it a quick highlights. Not sure why our highlights are a little bit too big. Let's try again. Weaving specification of a composite building block specifies how code generated by its member building blocks is woven together. We have found a code weaving specification language along the lines of J sufficient for our purposes. Okay, let's have a quick look at what J is all about. So, meta let's call this bibliography and say that we want to keep an eye on this chap. Let's put it dash here. So J seems to have some similarity with Stitch, and for good measure let's give it a nice highlight as well, so that when we bump into this again we know that we've seen it before. Right, so so this is basically code weaving specification language. Thus building blocks and abstraction. Those building block is an abstraction to specify our concerned specific meta model, multiple transformation. I mean, they are repeating this quite a bit, and model text transformation in a localized manner. This locality coupled with the composable nature of the building block abstraction enables reuse in different contexts. The separable nature of building blocks allows them to be treated as independent configuration items that can be stored in a repository for future reuse. Very clever. The process of model-driven code generation is realized to a post-order traversal of the building block hierarchy in 3 sequential steps, namely instantiation, transformation, and weaving. The instantiation step stamps out models and merges them. The transformation step transforms models into code snippets and generates weaving specifications for composing them. The weaving step composes the generated code snippets by processing the weaving specifications. We illustrate this process. Actually, let me just highlight these 3 steps. And I think this is probably worthwhile highlighting with green, maybe, because clearly we have a similar approach. We've done this bit. We illustrate this process in more detail for 2 sample platform-specific code generators, namely Model to Java, Model to JDBC, and the design strategies, Object Relational Map, and Audits. Classes that needed to be persisted are marked as persistent in the model. Some of the persistent classes need to be audited. These are marked as auditable in the model. A persistent class has a representation as database table. Several strategies exist to implement object relational mapping. An auditable class records history of its state changes. Auditing strategy varies from application to application. We model each of these design strategies as a building block and compose a toolset variant from building blocks corresponding to the required design strategies. One such composition is shown in Figure 4. The specification of these building blocks are given below. So here we are, Object Relational Map. This building block specifies object relational mapping strategies for a persistent class. I'm waiting for time, 26 minutes. Right, so here we got MDD, Java, JDBC, design strategies, audits, and object relational mapping, technology platforms, model to Java, query to JDBC. For each class C having its persistence property set to true, there should exist a table T having the same name as the class C, a key K having the same name as the class C, a maps to association between the table T and the class C, a key association between the table T and the class K, operations to create, modify, get, delete, basically CRUD, having operation association to each. For each attribute of A, the class each there should exist, a column. Okay, we got the gist of it. Transformation spec for each class C having its persistent property set to true, generate the query models. Okay, right, so now we're just going to do how to read and write to the database. Audits. This building block specifies how to maintain a persistent audit trail of the state changes of instances of the persistent class. Each persistent class has a corresponding audit table having a column to store timestamp of the state change operation, a column to store the pre-image, and a column to store the post-image. I quite like this notion of audit, actually. Audit building block. The paper proposes the creation of a building block responsible for auditing. Auditing. Clearly I can't spell. We could probably implement similar functionality in Dogen using facets. Backlog this as a story, and let's put a quote here. Should really have some snippets for org modes, sadly I don't. Let's just put this chap here. I know that on the row method they say you should never quote, but I find quoting quite useful actually. Additionally, each persistent class has its methods getImage, setPreImage, and setPostImage. The methods getImage gets the current image of the object. The method setPreImage sets the current image as preImage in the audit table. The methods setPostImage sets the current image as postImage in the audit table. Okay, we got the gist of it. Basically, we record the object before and after the changes, so that we know what the changes were. And then there's a set of strategies associated with it. So Figure 5 shows a part of a unified meta model for an application. We illustrate the composition process for using a simple input class called person. For want of space, we consider only the stub tree rooted at design strategies building block of Figure 4, starting with a model containing a single persistent auditable class person with attributes SSN and name. Instantiation of the person-object relational map building block produces the table and operations marked with O. Instantiation of the audit building block produces the table and operations marked with A. And figure 6 shows a contribution made by each building block to the input class during the instantiation step. It's more of an aspect-oriented approach, really, where the building blocks are being composed to form a final file. We don't really do that. We chose to do composition by generating facets. So I guess we should probably mention this. The composition proposed by this paper is akin to aspect-oriented weaving of blocks of text to form the final artifact. This is in contrast to our approach, which proposes such composition to be made via facets. We should explain the pros and cons of both. This is something that we should really do. Righty, so then the transformation step follows instantiation step. The object relational map building block generates the queries for the operations create, modify, get, delete. The audits building block generates Q++ methods, method bodies for the operations get image, set pre-image, set post-image. The design strategies building block generates the following weaving specification. So brackets, person modify, before get image, set pre-image, so a set of methods here. The weaving step follows the transformation step. Processing of the weaving specification generated by persistence building block in the transformation step produces the following code. Person modify, so you are doing the image stuff. We translates, okay, so let's get into the discussion then. We translate the model MU, that is an instance of a unified meta model MMU, to various software artifacts like Java code, JDBC code, JSP code, and a variety of configuration specifications in XML, as shown in figure 2. Limiting aspect weaving is only code, well, this is not the best English. Limiting aspect weaving only to code, no, this is actually correct English, I just can't read. Limiting aspect weaving only to code level artifacts would necessitate specialized weavers for Java, JDBC, etc. Each having separate joint point models. Also, this approach would necessitate some commonality over these joint point models so as to have an integrated Java application. With increased number of software artifacts to be produced, the approach becomes increasingly complex. Essentially, it amounts to building aspect infrastructure for each such artifact. We address this problem by specifying aspect weaving at the unified meta model level. Right, so it would be nice to capture this, because whilst we don't have exactly the same problem, we have a similar approach to solve the problem. We address this problem by specifying aspect weaving at the unified meta model level and performing it at the model level. Whenever possible. We, quite disappointingly, we managed to yet again highlight too much. Oh, it's interesting. It seems like I don't seem to be able to highlight just this bit here. Ah, better. Unified meta model enables specification of relationships between the various sub-modeling languages. A reflexive meta model framework, Metabolic Framework, provides the necessary infrastructure to define and integrate the various modeling languages of interest, and Meta Model Aware Transformation Framework provides the necessary technology to address model weaving requirements. Okay. See, I clearly did not highlight the P. This is actually a bug in PDF tools, I believe. It literally can't highlight the space, otherwise it takes on the next letter. Performing aspect weaving at the model level Also, whenever possible, results in reuse of model-based code generators, such as Model to Java, Model to JDBC, okay, the different code generators they have, as these code generators are specified at the unified meta model level. We foresee several issues when using building blocks. It is not clear which facets of a system deserve to be modeled as building blocks. Okay, I quite like the honesty here. There is... this is rather annoying. Keep highlighting too much. There is a need to investigate how the engineering aspects can be modeled and what the right kind of abstractions for modeling them are to satisfy the various ETs like maintainability, reusability, etc. For instance, does one model designed for better maintainability? How does one model? Building blocks may overlap each other, so I'm just going to highlight this because it's not going to catch me this time. Let's make sure we don't highlight that bit. This may introduce a dependency on the order of the weaving. In such cases, how does one ensure the properties of all building blocks holds after the weaving? Supporting separation of concerns using building blocks raises several tooling issues. This is clearly a common problem with us. Now what we do is we will just make all of these chaps red. Or pink at any rate. Because, oh interesting, even though one worked, the next one didn't. That's really strange bug. The modeling tools should be extensible to support new modeling languages. This is required to define new aspect models and relate them to the existing component models through model transformation mechanism. The model transformation tool should have adequate support for pattern matching and composition. It should provide support for incremental reconciliation of models. Performance of the tool should scale to cater to the demands of enterprise class applications. Okay, there should be tool support for intelligent debugging of the block level. Okay, another interesting issue. This is significant because building blocks are specified independent of each other and woven together into the final implementation of the code. A bug detected at the code level should be traceable back to the aspect specification. There should be support, preferably tool-aided, for testing building block. Okay. Since building blocks are independently specified, it should be possible to specify test cases for an aspect independently and compose the test cases to arrive at the system level test cases. Okay, I think it's ambitious, but it's certainly a worthwhile ambition to have. See if we can get our pinks to come through. I wonder if the moving of the page helps or hinders. Okay, so these 5 aspects are very important and we need them. We need to take a note of this, but I think let's just quickly issues with building blocks. These issues are similar to those we face in Dogen. So one, the level at which we model building blocks is hard to gauge. Two, it's difficult to determine where one building block starts and another ends. This is exactly the problem we've already had with I/O. Separation of concerns, building blocks raises problems with tooling, and tooling needs to support debugging building blocks. We can just call these BBs, we know what it means. Testing of building blocks should be possible in an independent manner. Something like this. Okay, summary. In this paper we presented an abstraction for reusable MDD components. We described how this abstraction can support enterprise business applications, product lines as a model-driven software factory. We described a partial realization of this vision using building block abstraction. We discussed some outstanding concerns and tooling issues. Despite many problems yet to be solved, we found that building block-based restructuring to our MDD toolset has facilitated easy customization of the code generators and has resulted in increased reuse across their variants. Worthwhile annotation. Our MDD toolset has been used to develop several large enterprise class business applications for the past several years. That's very good. These applications can be viewed as a vertical, specific product lines that have toolset requirements that are similar but not exactly the same. Earlier, such a customization request meant opening up the implementation of the impacted tools that required expertise of all tools to ensure the relevant changes are implemented in a consistent manner. Building blocks abstraction has enabled us to organize the development team along two independent streams, namely technology, but okay, right, so clearly, the usual dual track approach. Moreover, it has enabled all toolset itself to organize the product family. This is quite important. Moreover, it has enabled our toolset itself to be organized as a product family, wherein a tool variant can be composed from a design strategy and a tooling technology platform aspects of choice. I think this is quite key. Oh, this is rather painful. Let's try it yet again. We literally are dealing with a lot of highlighting issues at the moment. We either can't highlight or highlight too much. Containment of change impact due to localization and increased reuse due to composability have led to quick turnaround time for delivering a tool variant. Use of a higher level model aware transformation language has made maintenance and evolution of the product line easier. Okay, so I think that is it. We haven't done too badly, 40 odd minutes. So what can we say about this paper? So it's a very good paper, very interesting paper. We probably should follow the sort of the other papers that Kulkarni and Reddy have written. However, just this paper is sufficient to give us a very good view of what they've done. It's a shame it's not more directly applicable to what we're doing, but we can see that the sort of the proposal of building blocks has a lot of similarities with the way that the mass conceptual model works. So there's definitely a lot of meat here for us to chew on, I think. Okay, and that's all for today, I think. Thank you very much for watching.